My name is Dagmara Chmielewska-Śmietanko and I am working in the Institute of Nuclear Chemistry and Technology in Warsaw, Poland. As one of the co-authors, I would like to present invention entitled Method for the Vitrification of Fused Sorbent with High Active Elements Inbuilt in their Structure with Salt Gel Method. Nowadays there are more than 440 nuclear fusion reactors located in 30 countries, generating about 12% of the world's supplies of electricity. Most of commercial nuclear power reactors are light water reactors, in which light water serves as coolant, which removes the heat produced inside the reactor core by the nuclear fusion reaction. Moreover, water is also a moderator, which slows down neutrons that are realized in the nuclear fusion process. The main function of the primary water circuit is to transfer heat from the reactor core to the steam generators. Additionally, primary coolant loop is a barrier that captures any fusion product that escapes the fuel. Water is also the most common media used to store spent fuel after being removed from the reactor core. Fuel rods are being stored in ponds for over 20 years. There are two main sources of the radioactivity of cooling water in primary water circuit and spent fuel pools. The first one comes from the products of uranium fusion, which are realized to the cooling water from fuel cladding flaps. To this group, for example, cesium and strontium radioisotope belong. The second is the neutron activation reaction of corrosion products of reactor construction materials. In this way, cobalt radioisotopes are produced. All these radioisotopes pose a serious threat to the humans and the environment, therefore need to be removed from water. The spent sorbent vitrification was conducted using salt gel method. Tetraethyl orthosilicate solution was stirred with deionized water containing ascorbic acid, applied as a catalyst and complexing agent. Next, spent sorbent and sodium nitrate was added during the stirring process. Obtained salt was gelated by the evaporation of water under a vacuum and dried. Obtained materials underwent a thermal treatment according to the appropriate procedure. After vitrification of spent sorbent, which contains cesium or other radioisotopes, an amorphous material with some crystals identified as crystobolites visible on its surface was obtained. The composition of the material changed after thermal treatment, although the presence of radioisotopes in the elemental analysis of the obtained material confirms successful vitrification of the spent sorbent. Glass can be classified as useful for radioactive isotope immobilization when the element leaching rate from the glass does not exceed 10 to -5 grams per square centimeter per day. The most intensive radioisotopes leaching is observed in the first week of the extraction with water, and the level of the radioisotope leaching subsequently stabilizing with time. The maximal rate of radioisotope leaching from the obtained glass confirmed the stable binding of cesium in the vitrified material. The determined leach rate is significantly lower than reported values for cementitious and cement bentonite materials, which are used for radioisotope immobilization. This is also greatly below the limit for glasses that are useful for radioactive isotope neutralization. The management of sorbent with radioisotopes bound in its matrix is highly challenging. Among the many methods of radioactive waste immobilization, vitrification is considered the best. The main advantage of this method is possibility of the incorporation of a large number of the elements into the matrix and the production of durable and small volume waste, which in turn prevents leaching of radionuclides to the environment. Borosilicate glasses are the materials more widely applied to form the vitreous matrix. However, some of the fusion products, especially radiocesium, are volatile at temperatures much lower than that necessary for the glass to melt, which means that some of the radioactive cesium can escape from the matrix during the melting process. The sol gel method that requires low processing temperatures helps to alleviate this drawback.